Welcome to the fascinating world of gravity assist maneuvers. Today, we're embarking on an extraordinary journey to explore how spacecraft cleverly harness the gravitational forces of planets to accelerate and navigate through the cosmos. This remarkable technique is not just a clever trick of physics, it's a game changer that allows missions to reach distant destinations with greater efficiency, saving both time and precious fuel. Imagine navigating a winding road. Sometimes, you need to take a shortcut or leverage the terrain to your advantage. In space, gravity assists act as those shortcuts, enabling spacecraft to gain speed and adjust their trajectories with remarkable precision. So, let's dive into the intricate science behind this celestial strategy and uncover how it shapes our exploration of the universe. A gravity assist, also known as a gravitational slingshot, is a sophisticated maneuver used by spacecraft to gain speed and change direction by flying close to a planet. Picture a skateboarder riding a half-pipe. By skillfully utilizing the curve, they can gain momentum and soar higher than they could with sheer effort alone. In a similar fashion, a spacecraft approaches a planet with a carefully calculated trajectory. As it enters the planet's gravitational field, it is drawn in, accelerating toward the planet's surface. This gravitational interaction is not merely a simple attraction. It's an intricate dance of forces that allows the spacecraft to borrow energy from the planet's motion. By the time it swings around and exits the planet's gravitational influence, it emerges with increased speed, ready to continue its journey across the solar system. This method provides a critical advantage, especially for missions venturing into the depths of space, where every ounce of fuel counts. To fully grasp how gravity assists work, let's break down the process step by step. When a spacecraft approaches a planet, its trajectory is meticulously planned to maximize the gravitational interaction. As the spacecraft draws near, it falls into the planet's gravitational pull, experiencing a significant increase in speed as it descends. This is where the magic happens. As it reaches its closest point, known as periapsis, the spacecraft is traveling at its maximum velocity. After reaching this point, it swings around the planet, and, as it moves away, it is flung out into space at a higher velocity than when it arrived. The science behind this is fascinating. By aligning its trajectory with the planet's orbital path, the spacecraft effectively gains a boost in speed relative to the Sun. This process can be visualized as a two-car collision on a racetrack, where one car, the planet, is moving at a high speed and the other, the spacecraft, comes in from a different angle. When they meet, the smaller car can gain momentum from the larger car's motion, allowing it to speed ahead. At first glance, it may seem puzzling that a spacecraft can gain speed from a planet without consuming additional fuel. The key lies in the principles of conservation of momentum and energy. As the spacecraft approaches the planet, its gravitational influence draws it in, increasing its kinetic energy. In turn, the spacecraft exerts a minuscule gravitational force back on the planet. Although the planet is far too massive for this force to have any noticeable effect on its trajectory, this interaction results in a subtle transfer of energy. As the spacecraft swings by, it takes on some of the planet's orbital energy, allowing it to accelerate without the need for thrusters. This technique becomes increasingly valuable for missions venturing to the outer planets, where fuel is limited and solar energy is weaker. By making the most of these gravitational interactions, spacecraft can achieve extraordinary feats of exploration, often covering vast distances with relatively little energy expenditure. This method not only saves fuel but also extends the mission life of spacecraft, enabling them to carry out more scientific research along the way. Gravity assists have played a pivotal role in some of the most iconic missions in space exploration history. Take, for instance, NASA's Voyager program, which launched in 1977. Voyager 1 and 2 ingeniously utilized gravity assist from multiple planets, Jupiter, Saturn, Uranus, and Neptune, to traverse the vast expanse of our solar system. Voyager 1 gained an incredible speed boost during its flyby of Jupiter, which not only accelerated the spacecraft, but also provided invaluable data about the gas giant and its moons. The information gathered during this encounter revolutionized our understanding of Jupiter's atmosphere, magnetic field, and its extensive system of moons. Similarly, the New Horizons mission famously used a gravity assist from Jupiter to accelerate on its way to Pluto. By carefully timing its flyby, New Horizons was able to reach the dwarf planet in record time, yielding groundbreaking insights into its surface and atmosphere. The data returned from Pluto was unlike anything we had seen before, revealing a world of icy plains, mountains, and potential geological activity. These missions are a testament to the power of gravity assists in deep space exploration, showcasing how strategic planning and precise execution can yield extraordinary results. Planning a successful gravity assist requires precise calculations and advanced computer simulations. Scientists and engineers rely on sophisticated models to predict the gravitational interactions between the spacecraft and planets, ensuring optimal outcomes. These simulations are grounded in complex mathematical equations that describe gravitational forces and trajectories. Researchers analyze variables such as the spacecraft's speed, the mass and velocity of the planet, and the desired trajectory. Each of these factors plays a crucial role in determining how effectively the spacecraft can gain speed. For example, during the planning phase of a mission, teams conduct extensive simulations to ensure that the spacecraft will follow the intended path without risking a collision with the planet or other celestial bodies. They also account for various gravitational influences that may affect the spacecraft during its journey, including those from nearby moons or other planets. This meticulous planning is essential for ensuring that each gravity assist achieves its goals and keeps the mission on track. The collaboration between engineers, scientists, and software developers is vital, as they work together to create the most effective trajectories for their spacecraft. While gravity assists are powerful tools in a spacecraft's arsenal, they are not without limitations and challenges. The success of a gravity assist hinges on precise timing and trajectory. Even a slight miscalculation can lead to missed opportunities or diminished speed gains, jeopardizing the mission's objectives. Moreover, gravity assists are limited to specific planetary alignments. Not all missions can utilize this technique, especially if the planets are not positioned favorably relative to the spacecraft's trajectory. For instance, certain missions may require multiple gravity assists to achieve their goals, complicating the planning process. Additionally, as spacecraft venture farther into space, they may encounter various gravitational influences from multiple celestial bodies. This adds layers of complexity to the planning and execution of gravity assists, necessitating careful navigation to avoid potential pitfalls. The interplay of these factors highlights the intricate nature of deep space exploration and the importance of meticulous mission planning. Another challenge is ensuring that the spacecraft systems can withstand the rigors of a high-speed encounter. Engineers must consider the thermal and mechanical stresses that the spacecraft will experience as it swings close to a massive planet. Gravity assist maneuvers exemplify the ingenuity and resourcefulness inherent in space exploration. By strategically leveraging the gravitational forces of planets, spacecraft can travel faster and farther, unlocking the mysteries of our solar system and beyond.